Thanks, Emily. Hello, everybody. Phil Riley here. Thank you very much for joining us. The webinar comes to you from Ampcontrol headquarters in Newcastle, in New South Wales. Today's presentation is called Transformer Oil Analysis, Identification and Management of Abnormal Conditions. So power transformers are very important components of the power network. We find them on power generation sites in transmission and distribution systems, on industrial sites such as mines and refineries. They're typically filled with mineral oil, also ester fluids, and they can also be dry type. A well-manufactured transformer can last beyond 40 years. We routinely see older transformers still in service, and they're very reliable pieces of equipment. And reliability surveys based on standardized questionnaires developed by Seagray show failure rates are less than 1% for substation type transformers at voltages even greater than 300 kV, with generator step-up transformer failure rates reported to be slightly higher. And some experts in the industry believe rates of failure do increase as an asset ages. Let's go on to the next page. Thank you. So what I'll cover today is outlined here. Sampling transformers, the importance of doing so correctly, testing of mineral oil and alternative fluids, interpretation of results, recommendations to manage abnormal conditions. We have a few case studies to review, and we can take questions at the end. So let's begin with the process of taking samples, which is the starting point. So taking an oil sample from a live transformer once per year is an accepted, routine and cost-effective method to get a condition assessment of the asset. A high-quality sample is required if you want an accurate condition assessment of your asset. If you take your own samples, seek out training to ensure you're doing it correctly. You might already use Ampcontrol to take the samples for you. We're a firm believer in the use of 50 ml glass syringes for dissolved gas analysis and moisture testing. These are two important tests. Using a syringe helps us to avoid uncertainty if, for instance, moisture levels suddenly increase. So we can probably eliminate atmospheric moisture being the cause of the increase if the oil hasn't come into prolonged contact with the atmosphere. So the sampling equipment that you use must be very clean. Any moisture or particle contamination can, for instance, reduce the breakdown voltage of an oil sample. If this occurs during testing, how do we know if the result is because of a sampling problem and not a problem with the asset? You must also ensure you perform a thorough, vigorous flush before the sample is taken. Take a liter. We should try to avoid any free water or particles in the drain valve being sent to the lab. This can affect the results and the condition assessment. It's better to avoid sampling in heavy wind or rain, as this increases the risk of contamination of the sample, and it generally makes taking the sample more difficult, and working in the rain can increase the risk of slippage. For your information, ASTM D92315 can be used for guidance in sampling, and also Ampcontrol have a written sampling procedure that they can share with you. Follow necessary precautions as you're sampling from live electrical equipment. Hazards to include in your GSCA include uneven ground, slips and trips, exposure to HV and LV, snakes and spiders. I'll talk next about some of the tests we do on an oil sample to allow us to generate a condition assessment. So dissolved gas analysis, DGA, is a very important test that we perform. It's typically done annually and more frequently if a problem is identified, and we'll look at problems identified by DGA throughout the presentation. So faults in the transformer can deposit energy into the oil, and this energy can initiate formation of particular gases from the long chain organic molecules in the oil itself. And we extract the gases from the oil, and in the lab, we separate the gases using a gas chromatography system. And the photo shown on the right shows part of this process at our lab, which is called Verico. It's also in Newcastle. So let's quickly look at the other tests we can apply to assess the condition of the liquid insulation. Changes in breakdown voltage of the oil can be due to, for instance, increases in moisture levels in the oil and the paper insulation, and also because of breakdown of the paper, that can deposit cellulose fibers into the oil. Also, the equipment performing the KV test may be the source of the variation, and this applies to any test that's done on a transformer. So the KV of transformer oil needs to be sufficiently high to allow it to withstand the electrical services stresses imposed in service, and this includes ensuring that an arc is extinguished. The moisture content of the oil should be low, otherwise the electrical strength of the oil will be impaired, and moisture can be absorbed into the paper insulation, possibly reducing paper insulation life and also increasing the risk of dielectric breakdown. Sources of moisture in transformer oil include ingresses of moisture from the atmosphere, oxidation of the oil, acid catalyzed hydrolysis of paper insulation, and thermal degradation of paper. Elevated levels of low molecular weight acids can promote the breakdown of paper insulation, particularly when the moisture content of the paper is also high. High levels of acids can also lead to formation of sludge. Sludge can prevent dissipation of heat from the core and the coils to the insulating fluid if it sticks to the surface of the windings or if it blocks the flow of insulating fluid through the cooling ducts. Degradation of paper insulation can follow due to overheating of the system and also because of the acidic properties of sludge. So likewise with these other tests that we perform, we can identify abnormal situations that suggest problems may be occurring. Such results are a prompt for further investigation. If any test identifies an abnormal condition, our first recommendation is to retest to confirm the data. Finally, consider regular furan analysis to evaluate the condition of the paper insulation of the transformer, and I'll talk more about this later on. When we finish the testing of the sample from a transformer or a tap changer, then we move to the process of interpreting the test data. And here is a list of technical guides that we use in the interpretation process, and there are also others. So I've split them into DGA, liquid insulation, solid insulation. They come from the IEEE, IEC, Seagray, SD Myers. They look at the different fluid types, mineral oils, esters, silicon fluids. And the testing we do is from oil samples is largely interchangeable between the different fluid types. There are some differences. But we've integrated these guides into the processes we follow at Ampcontrol to perform the condition assessments. So this is our first case study. Let's have a quick look at the test results for this transformer. So Ampcontrol sample and test this transformer each year, but listed here are just the 2020 test results. So this transformer was manufactured in the UK in 1936. So it's 85 years old and it's still in operation. So the dissolved gas analysis results don't indicate any abnormal conditions. The dissolved oxygen levels are not low. However, the oxidation inhibitor levels are good. So we recommend you maintain these levels at 0.3%, particularly in older assets and when the dissolved oxygen levels are greater than 1,000 ppm. And under most conditions, transformer oil will not undergo oxidation, aging, if sufficient inhibitor is present. So this is guidance from SD Myers. The absolute part per million moisture levels in the oil are within acceptable levels, according to IEC 60422. They're not low. The percent saturation is approximately 38%, and above 30, the condition of the cellulose insulation may be extremely wet. And this guidance comes to us from IEC 60422. And because the percent moisture by dry weight is so high and certainly above 2%, this is another indicator of wet paper insulation, which may accelerate degradation of the paper. So these numbers will be monitored closely this year when the asset is retested. So the other oil quality test parameters are good: breakdown voltage, acidity, and IFT. In 2020, we looked at the paper insulation condition of the transformer by furan analysis from an oil sample. I thought it appropriate to do so because we had no recent historical furan test data, and because the asset is so old. So we measure the concentration of 5 furanic compounds in the oil via a technique called high-performance liquid chromatography. The source of these furanic compounds is the degradation of the paper insulation. The 2,4-aldehyde level concentrations are high, and we use the concentration of this to calculate degree of polymerization, or DP, via the Chendong equation. And there are other equations available to us that we can use. In 2018, Seagray Working Group D153 published Aging of Liquid Impregnated Cellulose for Power Transformers, and in it there's a reference that states above DP of 650, the tensile strength of the paper is expected to be similar to new paper. And with this particular transformer, the DP is less than 650. This indicates some paper insulation degradation has occurred. It's also higher than the DP of 200, which we consider to be approaching end of life for the paper insulation. What's also noticeable is the trace amounts of the other furans. We typically don't see this, partly because they have a short half-life. Their presence indicates possible active stress on the paper, including oxidation of the paper insulation. So annual assessment of paper condition by furan analysis, I think, is appropriate due to the age of the asset and also because of the generation of these other furanic compounds. In the next case study, we look at the transformer has a problem that's been identified by dissolved gas analysis. And here is a list of faults we can detect using dissolved gas analysis. So on the left, we see there are discharges of high energy, low energy, high temperature heating above 700 degrees Celsius, that's T3. Then there's temperature reductions, T2 and T1. There can be overheating, corona partial discharge, heating of the oil, which is stray gassing, and possible burning of the paper, carbonization. So let's have a look at D2, discharge of high energy. So if this can occur, as any fault can, in the oil or in the paper insulation, either way, the severity of the fault is very high. So this table is taken from a technical brochure published by Seagray in 2019. It's called Advances in DGA Interpretation. So the next case study we will look at has a T3 problem. That's high temperature heating, above 700 degrees Celsius, possibly. And if this occurs in the paper insulation, the severity is very high. If it occurs in the oil, the severity is less. So the transformer is 5 MVA, 66 kV primary. It's 23 years old. It's filled with mineral oil. So the paper insulation condition is good based upon the 2019 results. So the DP is 697, down to DP values of 600 to 700. The paper's mechanical strength remains similar to new paper. Now the most recent water and breakdown voltage levels are okay. The acid levels are not low, and levels are questionable according to guidance from SD Myers. And their classification system is more stringent than, for instance, IEC 60422. So this prompted me to recommend closer monitoring of furan test data to evaluate the effects of the acid levels upon the condition of the paper insulation. Decreases in DP would be a prompt, an additional prompt for us to recommend Fuller's Earth filtration to clear the oil of the acid. Now, the first time this transformer came to our attention is when we were sent the May 2020 test data, and we were asked for an opinion. So there was a big increase in methane, ethane, and ethylene levels between 2019 and 2020. This, according to the IEEE key gas method, looks like a thermal mineral oil fault. We looked at the data via Rogers ratio. It was inconclusive. So this is another interpretation tool we can use. Others include Duval triangles. So Duval triangle 1, the analysis of the data provided a T3 condition assessment, so that's high temperature heating. Duval triangle 5 was C, carbonization, possible burning of the paper. And we use triangles 4 and 5 only really after identifying a fault with triangle 1. Triangle 5 should only be used in case of thermal faults, T3 or T2, and we can use it to distinguish faults that are occurring in the oil or with the paper. And it's worth noting that the low levels of carbon monoxide and carbon dioxide don't really support the involvement of paper insulation in this heating fault, but it's possible only a small amount of paper insulation is involved. And on the next slide, we'll look at more information about T3 heating faults and recommendations. So this is the type of information we supply to our clients where we find high temperature heating problems in their transformers. So examples of T3 faults include large circulating currents in the tank and the core, loose connections in the high voltage winding circuit, overheated bushing connections, lead joints, problems with the offload tap changer. The risk of dielectric failure of the paper can increase if burning of the paper occurs. That's carbonization. The presence of acetylene in the sample points to either the severity of the fault or the involvement of electrical contacts. Our recommendations to manage these type of faults include, retesting the oil with a new sample to monitor the rates of generation of ethylene and acetylene. Also to look at any recent electrical test results that could give clues to the cause of the problem. If further large increases in gas levels occur, we'd recommend doing electrical testing such as sweep frequency response analysis, winding resistance testing, turns ratio testing. We could recommend taking the transformer, doing an internal inspection to investigate the cause of the gassing. We could look at online testing such as thermography to identify overheating points in the tank or the bushing connections. Certainly particle count testing from an oil sample to monitor the occurrence of burning of the oil, and furan testing to monitor the effect of the heating upon the paper insulation. So Ampcontrol did an emergency on-site transformer inspection. So the oil was drained out of the transformer to the top of the core to complete the inspection. The inspection cover was removed. The engineers who were on site took photos of the core and the tap changer assembly. The tap changer contacts were in excellent condition. There were signs of heating on the star point connection on the A phase. And also the engineer that did the inspection pointed out that there was some warping of the core. You can't really see it here, but that's something that we noted, which could be caused by something during operation. So the engineer decided that the best option would be to transport the transformer back to our workshop for further inspection and repair. So the internal inspection at our workshop in Newcastle identified a number of problems, including a partly unsecured and dislodged coil clamp block under the top core frame. We saw a small amount of arcing discharge between some of the core steel sheets. 4 hot joints in the LV leads were found, and we thought that these were the most likely cause of the high temperature heating faults in the fault gases in the oil. The hot joint observed on C phase was quite severe. The engineer conducting the inspection believed the hot joints were caused by inadequate preparation when crimping the copper lug to the aluminium winding conductor. The photo is of the LV-C phase winding connections. You can see the extent of the burning, and also there's this large crack here. So our workshop repair program, including replacement of damaged and incompatible materials that contributed to the heating problem, also a partial rebuild of the clamping structure. The core and the coil assembly were processed in a vacuum oven, followed by vacuum filling and hot oil circulation to further filter the liquid insulation of water, gases, and particles. Some electrical testing was conducted, and the asset was transported back to site, and it's still in operation. So as per Duval triangles 1 and 5, we did see a high temperature heating problem and also burning of paper. So we're asked the question, can we test transformers that are not filled with mineral oil? So this is some data from a high temperature heating case study. It's a different transformer and the asset is filled with a natural ester. And the DGA results are listed here on the left, and they indicate a problem is occurring. So really this gas here, ethylene, this is the really interesting gas indicating high temperature heating. So we analyzed the data via Duval Triangle 3 and Duval Triangle 7, and both give a consistent T3 thermal fault assessment, high temperature heating, going back to 2017. We can also use these triangles to identify other faults as well. So this assessment, high temperature heating, is also supported by the elevated levels of ethylene. And we see that the rate of generation has slowed in the most recent test results. And some gas levels have declined, including carbon monoxide. Acetylene is not being generated. This is positive. Its presence in the sample points to either the severity of the fault or the involvement of electrical contacts. Also, the ratio of CO2 to CO, carbon monoxide, is greater than 7. And this test data suggests that the heating fault may not be significantly degrading the paper insulation. And this reference is taken from IEEE C57155. Duval Triangle 5 suggests that the fault is located in the not located in the vicinity of paper. And so my point is that we can confidently identify faults by dissolved gas analysis in transformers filled with alternative fluids. Let's move on to a new case study. The transformer is 4.5 MVA, it's 33 kV primary, it's 37 years old. The dissolved gas analysis results on the left don't indicate occurrence of any abnormal conditions. The oxygen levels in the oil are high. So saturated oxygen in oil is approximately 25,000 to 30,000 ppm, and this can promote oxidation of the oil and accelerated paper insulation aging. At these levels, it's possible the transformer is free breathing. We don't know what the oxidation inhibitor levels are. They're probably very low or zero, judging from the acid levels. So let's look at the oil insulation results. The moisture levels are low. The breakdown voltage levels are high. That's good. The acid levels are fair. And the acid levels are fair, and the IFT levels are poor, according to IEC 60422. The acid levels are unacceptable, according to guidance from SD Myers. Now, lower IFT is an indication of oxidation or aging of the insulating oil, and the deterioration of the liquid influences, or it can influence, the rate of deterioration of the paper. So the furan analysis results give a DP of 608. So I think we're close to a point with this transformer where some real paper insulation degradation may be about to occur, and the acid levels are a strong candidate for the cause of the problem. So very quickly, I'd like to talk about acid and transformer oil. So where does it come from? The high levels of oxygen dissolved in the oil can generate carboxylic acid and other acids reacting with the hydrocarbon molecules in the oil. It's low molecular weight acids that are corrosive to paper insulation. And to the right of the page, we see the degradation of cellulose paper by water in a process called hydrolysis. The process is catalyzed by acid, which donates these hydrogen ions. And this furanic compound, hydroxymethylfurfural, further degrades to produce these low molecular weight acids. And we know from published data that formic acid is corrosive to paper insulation. So degradation of the paper insulation will reduce the life of your asset. And the key message here is maintain control of levels of oxygen, water, and acid in your transformers. Ampcontrol did a limited on-site internal inspection on this transformer after dropping the oil. The picture on the left is looking into a radiator via a bottom pipe. The orange is rust. We saw some paper in there from the windings, and you can see sludge at the base of the radiator. Likely this would be floating on top of the oil. We only inspected one radiator. The middle photo is sludge being pulled out of the radiator pipe. And the photo on the right is looking down on the top of the core, and we saw shiny metallic nodules, some of which had rusted. So very unusual. So where we test transformers and where the acid levels are elevated, so we pass on these recommendations to our clients. Certainly oil reclamation, filtration can be considered to remove acid and return the oil to a non-damaging condition. During any internal inspection, check for the presence of sediment and sludge, monitor the operating temperature and dissolved gas analysis. Look for overheating because sludge deposition can impede heat conduction from the windings. Regular furan analysis to evaluate the effect of acid on the condition of the paper. Check any thermography data to identify possible blockages of cooling areas due to the presence of sludge. Regular oxidation inhibitor testing to evaluate current levels. Remember, under most conditions, transformer oil will not undergo oxidation if sufficient inhibitor is present. Maintain low water levels in the paper, and oil as elevated levels can increase the breakdown of the paper by acid. Look, the paper insulation in a transformer is an electrical insulator. It's also a physical structure within the transformer. It separates the copper windings, for instance, and this is a very important role. On the right, we see the internals of a transformer that we were manufacturing here in Newcastle. We have a transformer manufacturing facility here. It's important and possible to maintain the condition of the paper in good condition throughout the life of the asset, and doing so can prevent avoidable reductions in asset life. Just a few more pages now. One of the recommendations I listed previously was oil reclamation, so I'd like to speak a little bit more about this. Now, reclamation is a life extension activity. It's applied to transformers where the oil acid levels are elevated. So we maintain a fleet of mobile acid filtration trucks. With the filtration process, we can remove soluble and insoluble polar contaminants from the oil via Fuller's earth, which is a naturally occurring clay. We can clear the oil in the windings and the cooling system of acid and sludge, and we return oil to as new specifications. And this can reduce the rate of degradation of paper by removing acid and water from the system. The photo on the top right is a schematic of the systems that we use to treat transformer oil. Oil is degassed by heating and vacuum, and water is removed here. The oil is filtered, and then the oil is passed through these Fuller's earth columns, and this takes out acids and other oxidation products, and the oil is filtered again. And the process is repeated, so the oil is pumped into the transformer very slowly, and this process of filtration is repeated until the interfacial tension levels rise above 35. And at this point, we know from experience that we've cleared the oil of sludge and acid, and we add oxidation inhibitor as the final step. And this is very important because it prevents re-emergence of acid. And the photo below shows you what a filtration system looks like. You know, it's parked next to a transformer. The work is done when the transformer's live. The oil is taken from the bottom of the tank, goes through the filtration unit. It's heated, and then it's passed back into the transformer, typically through the conservator. And the hot oil leaches dirty oil from the transformer core, and this dirty oil is taken to be filtered. And the technology that we use means the Fuller's earth can be regenerated up to 300 times by heating at approximately 600 degrees Celsius. So the process doesn't generate masses of Fuller's earth waste, which is good for the environment. Just to finish off, the accelerated aging of paper will reduce the life of the asset. The cellulose aging process is well documented. I've listed some available statistics about the effects of temperature, water content, and oxygen content of the oil upon the rate of degradation of the paper. So, for instance, 2% water content in the paper can reduce the expected life by a factor of 10. So look, these are just statistics. And if the transformer has any of these issues, then we advise you to monitor their effects upon the paper insulation by regular Furan analysis. We should look out for big reductions in degree of polymerization, or DP. So just to remind you, the DP of new paper post-dry out is approximately 1,000. Below 200, it's considered to be approaching end of life, and at this point, the mechanical strength of paper can be 30% that of new paper. Below these levels, the tensile strength, may be too low to resist mechanical vibrations and electromechanical forces produced by external short circuits. So this is what some people believe. Also, the thickness of degraded paper decreases with its DP, which can result in a gradual relaxation of coil clamping pressure, leaving the windings more vulnerable to possible dislocation or deformation during a short circuit event. So we advise you to monitor and control operating temperature, ensure correct operation of the oil temperature indicator and the winding temperature indicator, maintain sufficient levels of oxidation inhibitor. Ingress of moisture and oxygen can be controlled by repairing oil leaks, replacing gaskets, regular inspection of the silica gel breathers, use of a bladder in the conservator, and also water, acid, and oxygen levels can be reduced by filtration. We'll take some questions. Thank you. We'll take some questions. If you have any oil analysis reports that indicate a problem, please send them to this email address and we'll have a look at them for you.
Wonderful. Thanks, Phil. Always a very interesting presentation. So we have had a couple of questions come through. The first was just if the attendees could get a copy of the presentation. Yes, we absolutely can. We'll send that through when we send the email about the video. And how do you select which Duval triangle to use? So back on slide 8, where it was the case study of the transformer from 1998, in that case it was T3 versus C in that instance. So how do you select which triangle to use?
I guess if you're using mineral oil, that dictates the use of the triangles. If you use mineral oil, triangle 1 is your first point of call, and then if you have, say, elevated levels of hydrogen, you can go to triangle 4. That gives you more information about low temperature heating faults. You can go to triangle 5 if you have higher temperature heating faults. So that will tell you, that allows you to differentiate between, triangle 5 allows you to differentiate between the location of the high temperature heating problem, whether it's in the oil or if it's in the paper. And then if we use alternative fluids, we use triangle 3. If this identifies problems, there are further triangles in that series. So for instance, 7 that allow us to give us further information. And then triangle 2 we can use for on-load tap changes. So I hope that answers the question.
So the next question is, if after retrofilling the transformer with natural test oil, we are getting a DGA result showing a T3 fault, how will we know whether the temperature rise is due to fault or just because of local capability of natural test oil due to the high viscosity?
You shouldn't see a high temperature heating problem after you retrofill with a natural ester. So I think in this case, what we'd like to do is, if you could send us a copy of the oil analysis results and we'll have a look at them. But certainly when we do retrofills with natural or synthetic esters, we don't expect to see high temperature heating problems.
Great. Well, feel free to send that one through to fstech@ampcontrolgroup.com. That was from Anupan. The next question is, what analysis is recommended for non-paper insulation?
Oh, that's a good question. What does that mean, though, non-paper insulation?
Gary, if you're able to just expand on your question for us and just pop it in the question box, that would be wonderful.
And we can come back to you with an answer.
Yeah,
sorry.
Come back to you with that one. Do we have any more questions? Feel free to pop them in the question box. While we're waiting, I will just let you guys know that throughout the presentation, Phil mentioned SD Myers, which is a transformer maintenance methodology. Ampcontrol is actually running a training course at that at the end of August. So we will send you through some information if you want to express any interest in that when we send through some the recordings and the presentations as well. And we have also got 4 more presentations in the asset management webinar series, so one every week from this week. So feel free to have a look at those as well. Look here, doesn't look like we've had any more questions. We'll give it another couple of minutes just in case anybody's furiously typing away with their queries. There is also a number of presentations which will send in the information that Phil has done a number of presentations over the last 12 or so months in relation to transformer maintenance, particularly the oil perspective. So we'll include those and you can see those anytime on the Ampcontrol YouTube channel as well at your leisure. Are there any analysis results that point to lightning strike issues? That was a question from Gary.
Yeah, you might see a peak in acetylene levels. That's a very good question. So where we see a sudden increase in acetylene levels up to maybe 5 parts per million, particularly with no other heating gases such as ethylene, then that could point to a lightning strike. Yeah, so that's a very good question. Particularly if the transformer is connected directly to the overhead lines as well.
Great question, Gary. We haven't had any more questions, so we might just give it another minute or so. So if you do have any more questions, feel free to pop them in the question box. But if not, again, thank you very much for joining us. We hope you found the webinar interesting, and we hope to be in touch with you soon. So
thank you. Thank you.
Would this testing begin? So at what point in a transformer's life would the testing begin?
Well, the testing begins in the factory when the transformer is manufactured. So you do testing, acceptance testing in the transformer factory. That information should be given to the asset manager. And then on an annual basis, we think from day one that the transformer should be tested via oil sampling.
And that's a pretty cost-effective alternative method to, huge problems later on down the track.
Yes, yes.
All right, well, if you do have any more questions, feel free to send them through to fstech@ampcontrolgroup.com. We'll be happy to answer anything you might have, and have a wonderful afternoon. Thank you, everybody.